Now, just now, before the break, we talked about the GILDS model, which is quite helpful when you want to explain about the atmospheric corrosion. All right. Next, we talk about the layer by layer, right? So we go into deposition zone, which is here, right? So what happened in this zone here, just above the solid, right? Above the solid, you have a deposition and the exchange of electron here. So deposition layer, what happened is that you have a table to refer to. So this deposition, you have all these species, right? You have all these species that you can find on this layer, depending on the material of the source of your solids here, right? So if you're aluminium, you have all these lah. You have OL, OH, and so on. You can read from this table. So if you have ferrum, you have FeO, and so on. Copper, you have this one. Zinc, you have this one. Okay. So you can read from this table. So rarer species means sometimes you can find, sometimes it's not there, right? But common one is all this. Okay. All right. Now this table is important if you go into the corrosion. If you go into the corrosion research, then you all this is your focus, right? Even finding the rare species also can be your master research if you're interested in corrosion engineering. Then your area of focusing on the rare species rather than the common one, or it depends on whether you want to make more common species or want to find the rare species and find out what contribute to all these rare species. Okay. Important variables in the corrosion, again, there are a few. I'll just give you all the answer. So for atmospheric corrosion, just now we talked about the diagram, all right? The 6 layer. So this 6 layer actually can affected by all these factors. The time of wetness means how long is exposed to the humidity. So again, I use the word humidity rather than the solution, than the liquid solution. When your metals dip into solution, it become aqueous corrosion, which is in chapter 2 already. So chapter 3 is more on the humidity, moisture. We use a lot of moist, the word moist or humidity when we talk about wetness. Then sulfur oxide is also another agent to control the rate of the atmospheric corrosion, chlorides, contaminants, and temperature. So basically, you can group this one into time of expose, then the agent. So agent will be sulfur, chlorides, contaminants. Another one is the temperature, right? Time, contaminants, or time. Yeah, you can put this one as contaminant. Time, contaminants, and temperature. Okay. So the more time you expose to the humidity, especially when you have the critical humidity level, then the electrolyte will be formed on the surface, on the surface of the metals. Then the electrolyte layer will control the electrochemical process time. Okay. Then for the sulfate oxide, what does sulfate oxide contribute to the atmospheric corrosion? Or where does this sulfate oxide come from? It comes from the combustion process, from the fossil fuel. Fossil fuel means you can think of the engine, you can think of the automotive cars, factory, and all this. So again, previously we talked about four types of atmosphere: urban, lunar, urban, industrial, and marine. 4 types of atmosphere that we mentioned previously. So under urban and industrial atmosphere, you will have the problem of sulfur oxide or sulfur oxide. Okay? Why sulfur oxide is a critical contaminant? It is because they can absorb on the metal surface, and they are highly solubility in the water. Especially we have in the water means that when you have a moist, you have the H2O molecule, they're going to go and grab the H2O molecule. And also sulfur oxide, when they form with the water, they will form acid. They will form acid. The name, when you combine sulfur oxide and water, the chemical reaction, the exchange of electron, negative, positive, then you will get acid products. So when you have acid products on the surface, you know that when you have acidic surface, the corrosion rate will increase. So this is the cause and effect. So okay, when you answer the engineering corrosion engineering question in test or final exam, you think of the cause and effect. What caused the things? What can this thing do? And then you explain the process. Okay? So this is the chemical formula. When you have sulfur oxide combined with oxygen plus the 2 negative, again, you ask yourself, where can I get negative charge? Always from the metals component. You still remember we have one general equation for the metals deposition, or for the metal breakdown equation. M power n plus n e negative. That is where you get the negative charge. Again, for corrosion, there is no external supply of electricity. All the electricity come from the breakdowns of your metal or alloy element. So SO2 plus oxygen plus charge, you get SO4, 2 negative. Okay. This one contribute to the acidic behavior. Okay. Okay. So these are the products lah. When you have metals, you combine with sulfur oxide reaction, you will get FeSO4. Okay, you get FeSO4, or another name is iron sulfate. So when iron sulfate, this one, FeSO4, combined with the moisture in the atmosphere, so FeSO4 plus the moisture, H2O in the atmosphere, you're going to form a new products. You get FeOOH, FeO, one partner, OH, one partner. You know that in chemical, you know that there's a covalence relaxation. So you have one product, this one, plus the sulfate charges, plus the hydrogen charges, plus the electron. Okay, so this one, when FeSO4 plus water, you will get charges. You will get a breakdown of the electron. So basically, you are contributing electron already. So when you have an electron, then you have anodic Catholic process reaction from there. Okay, then you have oxygen plus. What happens if you have oxygen plus? You recall back the definition of pH that you learned in your chemistry class. What mean by pH? What mean by acidic? What mean by alkalic? So just a recall what mean by the pH value. pH value influenced by 2 chemical charges. One is H positive, one is OH negative. Okay, so okay, let me do the zone. So you visual, this side is negative, right? So this is a neutral. Then you go to this side is acid, right? 7 to 1. So this side, when you have more H positive, it will contribute to the more acidic area. When you have more OH negative, it will go to alkaline value. Okay, so this is just a fundamental concept of what is pH level, right? What is pH? What is pH level? Why you see a low number of pH? Why you see a high number of pH? It is because of the H positive and OH negative. Right? So in this case, when you see H positive in the equation, it means that it will contribute to acidic condition. The pH will drop from neutral to a little bit of acidic. It won't straight away jump into an extreme pH level, but it will change from normal 7, maybe drop to 6.5, 6, and so on, because of H positive. Huh? Okay, so this is about the sulfate oxide. What about chloride? Chloride also another pollutant, or you can say another contaminants or chemicals that contribute to the corrosion. Again, you need to recall back what you learned in your chemistry. So, example of chlorides will be NaCl and magnesium chloride. So we call them under, or another word for chlorides is salt. Salt, NaCl, natrium chloride, natrium chloride, salt, magnesium chloride, also salt. But these two types of natrium or magnesium, they are gyroscopic. Gyroscopic means they like to capture moisture. They like to capture H2O molecule in the environment. Okay, so these two are very dangerous. Not dangerous, but these are the two bad guys when it comes to corrosion. They will go and grab water molecule to form acidic environment, right? Okay, so yeah. So I think I have the equation. Okay. So okay, so this one. So for forest, chloride will compete with hydroxyl ion to combine first cation. So again, this chloride, it will fight with the hydroxyl. What I mean by hydroxyl is the OH negative. OH negative is the one that contributes to the alkaline pH value. This chloride will always go and fight with this OH. All right. So on the metals, in the case of OH negative ion, okay, in ferrous, if you have a OH negative ion, basically they are more stable. They are more stable, and I mean the products, the species, when you have combined with the hydroxyl OH negative, they will become more stable. When you have an ion chloride soluble, means that the you imagine NaCl combined with the moisture with the water, then it will help the corrosion attack. Right? So OH negative is actually is a good thing to see, because it tends to form stable products that it somehow protect the metals or alloy surface. All right, because you know that again back to the pH definition just now, the more H positive you have in the solution or in the environment, you will drop your pH to the acid level. When you have a OH ion in the environment, more OH negative means you become more alkaline. Means it will help to protect the the surface. So chloride is not good. Chloride is something that will create acid condition. Another contaminants, for example, hydrogen sulfate, hydrogen chloride, and also chloride also. This one from the products of the industrial environment. So I just extract one of the important element. For example, hydrogen sulfide. Hydrogen sulfide, they like to mix with metals. They like to decompose the metals to break the metal into positive charge and contribute negative charge, right? So this one is quite a headache when you are in the heavy industry, because this is one of the products that you produce in the heavy industry area, right? So you need to have a very good corrosion engineer there, right? Nitrogen compound, or NOx. NOx means nitric oxide. Nitrogen compound with NOx, they're going to help the corrosion process also. Okay. And temperature, you know that if you increase temperature, corrosion will happen faster, right? So this is just an elaboration of what if you change the temperature. Right? Later, chapter 4, we look at the effect of temperature. Okay? This is just an introduction point for you. Okay, so is there a way to measure or quantify atmospheric corrosion? Of course, yes. The common one is they use ISO standard. So these are all the ISO standard. For example, there are long lists of ISO standard for corrosion, especially under atmospheric corrosion. They are long lists. This is just a few examples. For example, if you want to talk about classification, then you refer to ISO 9223. So under ISO standard, they will tell you how to test, how to identify what are the value, what are the reference standard value of that for that atmospheric corrosion. Okay. Then, for example, ISO 9224 is about values for the corrosivity category. Okay. So if you read the journals that I present in the previous class, the Malaysia corrosion report, inside there is one of the data show you corrosivity value. So they all referring to ISO standard, right? So all the data, how they capture the data, they follow ISO standard. Okay. Then the rest you can read from here, right? Next one will be, this is how you apply the ISO standard, right? So you start from the upstream. So you, under atmospheric environment, let's say you go and use ISO 9223. So refer back to this table. ISO 9223 is on the classification of your classification for your corrosivity. So you start from the environment, then you do data collection. Under this ISO, there are lots of guidelines to how you collect data and so on. So you collect data, and then you run the formula given by the ISO or algorithm formula, mathematic formula, how you calculate. Then you evaluate the data, you come up with a graph, chart, color, like what I showed you previously. You put them into high, low, medium, and so on. Then you classify based on the standard. and you process the data further. Okay, then you come up with a solution to solve the corrosion. Okay, it's a corrosion rate. So how to calculate the corrosion rate? When you want to do coating, want to do protection of corrosion, then you propose based on your data, and you beside the coating, what you can do is that you can look into the metals or material that you use. Okay, so another side will be on another test is exposure test and measurements, right? One is more on the evaluation of your data, one is more on the collection of your data. Okay, all right. So those if you are doing the FYP, so this is one of the example of flowchart, how you collect your data, how you process your methodology. All right, so there's if you have a handbook, if you have a guidelines, if a standard, for example, ISO standard to do things, then you just use the ISO and follow along the design process. Okay. All right. We will continue our lecture. We will look at natural water. Right. We will look at natural water. We have concluded the atmospheric corrosion already. Next, we will look at natural water. Then after natural water, we look at seawater. After seawater, we look at soil. What happened in the ground? How corrosion happened in the ground. Okay, so next lecture, we look at natural water. Okay, let me stop the recording. Let me see the time. Okay, I think we continue because we just spent about 20 minutes. Let's see. Okay, let's go into. Is that okay? We continue the class?
Yes, sir.
Okay, now.
Yes, sir.
Yeah, because I saw the time. Only 20 minutes. All right. Okay, let's go into natural water. Then maybe next class we look at seawater. All right. Okay. Now, why under corrosion we look at natural water? Because this is the thing that you will see or you apply when you go into industry, especially your manager or your boss asks you to put you in the corrosion protection or engineering department. Right. Natural water is important for the industry. Some of the usage when they pump water into the factory, they pump into water into the machine. The most popular application is cool down the machine. They have some combustion process, and then they want to cool down, or they want to create new energy, or they want to create they want to change the heat energy into mechanical energy. So they need the steam phase to turn the blade and so on. So natural water is one of the tools they use in the industry for cooling, for power generation, and so on. Okay. However, because you have a water, you know that corrosion is involved with metals, water, hydrogen, oxygen. So when you have water, then we have lots of things to talk about when it comes to corrosion. So when we talk about water, we need to remind ourselves they have a few unique properties. First one, they're able to dissolve. They're able to dissolve, we can say almost 90% of the substance on this earth. Can say almost everything really. Okay, you want to dilute, you want to dissolve something, you add water, right? So when the water that you capture from nature, especially when you have something like this in the dam, you release the water, you will capture some pollutant in the air because of they're able to dissolve, capture element. So in the water, you have impurity. So this impurity will contribute to the corrosion, right? So one of it is oxygen. when you have more oxygen capture in the fresh water or in the natural water, then in the process of corrosion, you have more concentration of oxygen, then the corrosion will happen, right? Let's do some review on the hydrologic cycle or the water cycle. As you know, right, let's go back. Okay, so you can see the evaporation from river, then go up, chain phrases, become rain, and then rain come down, go into the soil, one go into the soil, one go to the river, then go into the underwater, right? Go into underwater, and the cycle keep repeating. One of the worries or concern is something in the atmosphere that when the water evaporate, it captures something in the atmosphere, then it go into the soil. So the soil, inside the soil, you know that you have mineral, right? So inside the, wait for the graphic to come. Okay, inside this soil, you know that inside soil you have a different mineral. So some mineral is good for our body, some mineral is good for the process, but some of the mineral, it will create or it will activate the corrosion process, okay? Next, because of the impurity, we will introduce the purification process, or we call it water condition techniques when it comes to corrosion protection, especially when it comes to natural water. So one of the area we look at is the purification process under corrosion. I mean, how we control corrosion when we use natural water is that we do water conditioning, right? So this is a schematic diagram, not up to scale, but when you go into industrial area, you will have the fresh water that pump from somewhere, can be from the sea, from the river, from the well, from the natural resources, right? Then you go into the factory to cool down the engine, to cool down the machine, or even to generate power. Then you keep on recycle, and you put into the treatment plant. There will be some treatment plant nearby. Okay, then the treatment plant will distribute back to the environment. Okay. One of the criteria when we talk about water conditioning or purification or water treatment is that there are a set of tests when you want to release the water into the environment. Okay, so what are the tests? So these are the list of the impurity in the water treatment. So I'm not going through all these lah. So this one you have, I put all this in the tutorial handouts already, so you can read during your revision time. Okay, so you have on the left hand side, you have the constituent, means the area of your test. For example, hardness test, alkalinity test, pH test. pH I think is more relevant to you, right? You can relate very fast. pH test, sulfate, chlorate, alkalinity, hardness. So later we will look at hardness. Then the second column will be the formula that they focus on in the treatment, what they focus on. For example, the one that we'll talk about later is hardness. It focuses on calcium, magnesium, and carbonate, right? CaCO3 carbonate. pH, again, pH, H positive. H positive is more acidic. Yeah? Again, just now I introduced you the pH value, right? So the more H positive you have, it become lower the pH or become more acidic. If you have OH negative, it become more alkaline. But for water treatment, we know that acidic environment is more harmful, so you focus on acidic, because once you get your pH H positive, you can actually define another site, because once you have the pH value, you know that whether it's acidic or non-acidic, right? So we focus on H positive in this test in the water treatment. Just now we also cover the chloride effect, Cl negative. Difficulties cause you can read lah. For example, free mineral acid, you have a corrosion, and all these you can read. And the means of treatment, so how do you treat? For example, I take this one, free mineral acid, it will cause corrosion. How do you treat? You neutralize with alkalides if it's come from free mineral acid sources. So these are the methods to solve the things. Okay, so have a read through all this table. There's a long table, so spend some 5 minutes, 10 minutes just to read through the tutorial handouts. So yeah, I don't think we need to go through everything here. So you go and read. Okay. So this one, another page of the table. For example, okay, oxygen. I'd like to highlight because this is a very popular element. If you have oxygen, then corrosion in the water lines, heat exchange equipment, boilers will have problems. If you have too many oxygen, also not good. So what do? The treatment will be, you put in sodium sulfite, you put in inhibulator. Corrosion inhibulator means there's a chemical that protect the generation of oxygen, for example. This one is what? Aeration. Aeration means you take out the oxygen, right? Aeration means you take out the oxygen in the process. Okay, so this one you can read a lot of information here. Another page. This one is for another page from the table. So quite a lot of things, quite interesting reading. So you can read. Okay, one thing catch my attention is this one. Hydrogen sulfate. Chemical formula that we interested to study is that H2S. Because why? This is the one that you can detect with your senses, with your 5 senses, especially your nose. It will cause rotten eggs smell, corrosion. So if you read Malaysia news, I think last year or last 2 years, we come up from in the news that when resident area is too near to chemical process plant, they will have this problem. Okay, if they do not do water treatment properly, the residents will have this problem. Means they will smell rotten eggs. This one, and then they will complain to the Department of Environment. Then they go and check. Right, normally happen to the main cause of all this smell is because the factory do not properly do treatment, water treatment, the one that discharge back to the natural, then this one will happen. Okay, so I think you can relate this one when you drive car through some heavy industry area. Sometimes you will smell this one also. Right, it's because of the hydrogen sulfate element is there. And the treatment that you can do is aeration. Just now we see is de-aeration. This is aeration, means you pump in oxygen. You pump in oxygen, then you will break down the hydrogen sulfate. You do chlorine, you put in chlorine, and you exhibit or you encourage the anion exchange, something like that. Okay. So quite interesting when it comes to water treatment, but we won't go through everything. So again, go and read all this table, and have some idea what can it contribute to corrosion if you do not properly handle your water. especially if you're in the industrial area, water treatment plant and all this. Okay. Okay. Methods of water treatment in the table just now. In the table that I give you a long list, they basically consist of two methods. Either you use chemical or you use a physical treatment. Okay. Chemical means quite direct, means you add in chemicals compound. To do, for example, the water is too hard. Later we look at the water hardness. You soften the water and so on. Physical treatment is like you use carbon, you use silicon, you use the natural fiber or nanofiber to filter out the pollutant. Okay, this is physical treatment, means you use some devices that you filter water or you filter out the harmful element through the porosity or through the pores or the holes or the gap between the material. Right. The earlier technology, they use carbon, or if you study survival kit, they put in carbon, they put in stone and all this. So to filter the water. So that one fall under physical treatment. Okay, chemical procedure is more on the application of chemical products, right? So all this you can read from here. And what mean by successful water treatment? There are three or four. There are three. Okay, so three criteria for a good water treatment. First is that you achieve your target process, meaning, for example, you want to reduce the ammonia, you want to reduce the rotten egg smells, for example. Okay, you see whether you're able to remove the smell or not. Okay, so if you're in the PJ area, right, or Selangor area, I think a few months ago, we have some problem on the water treatment plant that it affect a major area in the PJ towns and also the Selangor some area. So they have to stop the water supply and yeah, so it affect everyone alive there. Okay, so this is also one of the criteria they're looking for when it comes to water treatment. First, target process, and then whether or not it can able to protect or slow down the corrosion. Whether your water treatment, the treatment that you do, whether it able to generate a protective layer or it able to stop the corrosion. The next one is that are you able to preserve or maintain the water quality? The water quality, meaning after treatment, for example, the water that you pump into your factory is a neutral pH, right? pH 7, or maybe a little bit of alkaline or a little bit of acidic, right? So after water treatment, the water must maintain like what you get just now, or even become better. Okay, don't after treatment it become more acidic, then you do not meet the criteria for successful water treatment. So these are the three general criteria when we talk about good water treatment. So again, there's a more table to look at. This is a method of water treatment. So you have two: chemical procedure and physical. So you can read. You can read. So go home and read. This is your homework. Yeah, go and read. Don't be surprised I ask something from the homework that I asked you to read. Okay. Another one is water pollutants. Okay, water pollutants. There are some gauge or indication for the type of water analysis. So this table is some value we use to classify the quality of water. Let's look at a few terms here. Result in ppm. What mean by ppm? Particle or parts per million. Parts per million. Meaning, if you parts per million is a chemical unit that you, when you do tests, meaning in the under microscope, if they count the particles in a million, let's say you have this number 40 ppm means you can find 40 particles in 1 million particles. Means in one sample size of 1 million, you can find 40 inside the sample. Okay, means you take a drop of water, you put into the instrument will pinpoint the sample that you have. Let's say that drop of water you put on the slides, and then you will count, right? In the space that you have, under microscope, you will count how many particles of your interest. For example, you will count calcium, you will count sulfate, you will count chloride, silicon, and so on. Okay, so this is an example of table they use for analysis. And then they group them into category. You have A, B, C, D until G. What I mean by A? Very soft lake water. G means very hard water. From soft to hard. So there is a value to describe the condition or the quality of the water. Okay. So if you're given, for example, I pick one. For example, pH. If the pH is lower than 6.3 or very near to 6.3, you say that the sample that you send for test is very near to very soft lake water. So if you send the water sample in and then the test result is maybe 7.1 or maybe 7.2 or maybe 7, around this value, right? 7.2 or 7 or 6.9, something like very near to this, or 6.9 is here already. So about this 7.1, 7.2, then they fall under E. What is E? Refer to this one. E is hard borehole water. Then when you get 7.1 pH also, it can fall under very hard groundwater. You have two repeated value here. So once you have repeated value, what do? You check for other profile. For example, if you get in the result, you get 7.1 pH, 7.1 pH, you fall under pH is fall under two category, right? It fall under E and G. So what is E? Hard boiled and very hard groundwater. Then to further define the water, you check other parameter. So maybe you check the second one, alkalinity. So under 7.1, one is 250 and 470. So you check the value of that sample. So if that sample fall around this value, it fall under E category. Means that sample is hard pore water. Okay. G is something. Okay. So what kind of question that we can come up from this table is that we'll give you a scenario, give you a table with the value, and then I ask you to identify the type of the water or the quality of the water. It's like I give you a map here, then I give you a location, a GPS location. You go and find where are you. Okay. Any one of you don't understand what is this one. You don't know how to read this table. You need more explanation, then I can explain. Any one of you, You have difficulties reading this table, or you don't know how to apply this table.
Sir, actually, if you can just repeat again or explain a little bit more, it will be better, sir.
Okay, all right. Now, this table, if you look at the topic here, the measurement is in ppm. ppm means what? Parts per million. Means you take a drop of water, you put into an instrument, it will count how many particles find in the million sample, right? So they come up with the formula already. For example, one drop of water got how many molecule inside there. They can count chemical, use a chemical calculation. So all this value is part per million. So this table give you on the left hand side the criteria or the area of your test. You can test your water using pH. You can test your water on the alkalinity. You can test your water on the hardness. You can test your water on the chloride, silica, default solid. Okay, this is only a short list. I just now I give you a few table underwater treatment. There are lots of criteria to that, and under ISO standard, there are lots a long list. This is just a very, very small list I capture from the table. Okay, so when you do water analysis, there are lots of criteria. This is only like 1, 2, 3, 4, 5, 6, 7. Only 7 area that I pick up from the list table just now, right? In the water treatment table, there are lots of lists, right? So I only pick 7 over here, and you can group. Okay, you can group your criteria into different family from A, B, C, D, E, F, G. Okay, so so for example, how you know it is A, or what is A? A is very soft lake water. B is moderate soft surface water. C is slightly hard river water, and so on. Okay, and all this value will give you some idea what is the sample that you send in. What is the sample that you send in? What is the quality of the water that you collect from that site? Okay, so all these are the value that you can refer to. For example, okay, for example, you send in a sample, and the sample give you pH pH 8.2. So what kind of water that you have? If you send in the water sample and the lab give you a pH level of 8, maybe 8.2, 8.4, what does the type of the water you have? Are you able to answer? Ngan, what type of water you have? If you have a pH 8.3, 8.4, 8.5, what type of water you have?
The slightly hard borehole water.
This one, right? F, right? Under F, right?
Yes, sir.
Okay, right. So your answer is under F, and then you read what is F. So it's over here, all right? So if the water pH is, if the pH, let's say I pick the very drastic example. Let's say that you send in the sample into the lab, and the lab first line in the report, it gives you pH 7.1, 7.1. So from pH level 7.1, it gives you E and G, right? So what is E and G? You read from the legend here. E is hard boiled water and very hard groundwater. You have two possibilities if the pH gives you 7.1. But if you want to further identify what type of water you have, you look for second parameter. It can be either one of these 7 factor here. For example, you go for test for alkalinity. If the first row in your report you get 7.1 pH, you have two possibilities. go and test other factor, other area. For example, you test for alkalinity and you come, the value is maybe 300 for alkalinity. So 300 is very near to E rather than G, right? The value maybe is 300, let's say 300. So it will very near to 250 than 470. So the sample that you send into lab very near to the E category, which is hardball whole water. Do I answer your question just now? Just now, who asked me to re-explain the table?
Yes, sir. Yes, sir.
Okay. So again, if you know how to read this table, basically it's a full mark, not full mark, it's a free mark question. Basically, just playing hide and seek, and or I give you a map and then go and locate yourself. Where are you in the map? Okay, I give you a scenario, I give you a table with all this pH value, silica value, and try to identify the water analysis results, right? So what are the type of the condition of the water, or what are the source, or what are the type? In this case, it's more on the water hardness. This is water hardness test. How soft is this one is a quantified data, means you quantify the hardness of the water. How hard is that water? Depends on all this value. It can be very soft, it can be very hard. Okay. Okay. Soft and hard is very subjective, but in scientific way, we can quantify with values. Okay. Yeah. Okay. So this is how you communicate in the engineering community. All right. How soft is soft? How hard is hard? So you quantify with a value here. Okay. Next one. A few pollutant that we need to be careful when you run the water treatment, or when it comes to pollutant, some interest area. So we're going to look at 4 areas. 4 areas when it comes to natural water. Natural water, there are 4 big group. When you talk about pollutant, we talk about a corrosion element. First, gases. Second, mineral. Third, organic matter. And micrological form, this is a bacteria. Okay, so these are the 4 I highlight with the blue color, means they are the main keyword when you explain about the constituents that you need to be careful in the natural water, especially when it comes to water treatment. So you can group into 4 categories. One is on the gases, second on the mineral, third one is on the organic metals, third one is more on the microbiological form, or in other words, is bacteria or single-celled alga or something. So first one, I already highlight all the important point there. You can read. So gases, you know that you have nitrogen, the oxygen, ammonia, and sulfur gas. All these contribute to the corrosion, right? And then material, you have, for example, bicarbonate, nitrate, sulfate. Later, I'll give you more information about this one. Organic metals means you think of the agricultural, right? Pesticides and all this, synthetic detergent, all this. And then another one is more on the bacteria, or more textbook word will be microbiological form. Okay, let's look at the first one. Under gases, most of the case start corrosion will be oxygen, right? So oxygen, it will contribute, oxygen concentration, it will contribute to the saturation, and the concentration in the water you can see from the appearance of green algae on the surface or in the water, right? Or the natural water. So you see the water, Some water, why become black color, why become green color, and so on, right? Why some water is very clear water, okay? Because of water oxygen concentration. Another one is this table. Oxygen have different level, different level of solubility, depends on temperature. So table 1.4 is about temperature, how it affects oxygen in the water. So you can see from this table, 0 degrees C, 0 degrees C, you compare concentration, they have two units. One is in part per million, one is in mole. This one is more in chemical. If you're a chemist, then you like to use this one. Huh? This one is more to the normal user, parts per million. Or you work in a factory, normally the QA department, they will use this ppm. So concentration, you can see if you have 0 degrees C or ice water, the concentration of oxygen in the water will be 14, about 14 or 15 parts per million. However, if you go and increase the temperature of the water, the concentration of oxygen drop 50%, from 14 drop to 5. If you increase from 0 degrees C to 30 degrees C. Okay, concentration drop almost 50%, 14 to 7. You look at the mole concentration also in the unit of micromole per liter. Okay, I believe you know what is definition of mole. 1 mole equal to how many molecule, right? So if you do the test of oxygen in the water at 0 degrees C, you get 400 something micromole per liter, and you increase the temperature to 30 degrees C, you see it agree with the ppm value where it dropped 50%, right? 455 to 236, almost half of this one. So this explain from this table, it explain the temperature can affect your solubility of the oxygen in water. Okay, so that's why also it explain why in the winter, if you're a 4-season country, why in winter you cannot grow crops and so on, and why algae appeared in the tropical hot country, right? And so on. So different countries have their own problems when it comes to natural water. This one is another chart for you about water solubility. This one is in seawater. Just now, this one is in air saturated water. You have all these value, air saturated water, or you can treat it as a lab control sample. This one is in seawater. In later chapter, later section, when we talk about seawater, then this table will come into the picture. So as you can see here, this seawater in a normal atmosphere. So what happened if you increase your temperature? What happened to the value of your, let me see, this one is salinity. Later we have one equation to calculate salinity. As you can see, the oxygen ppm 0 degrees C in seawater is 12 point something, and if you increase to, if you increase the temperature to 30 degrees C, the oxygen available in the seawater also drop 50%, almost 50%. Right, 12 becomes 6. Okay, so it's almost agree with the percentage of your chlorinity and also salinity, right? So let's say you have a very perfect case, 0, 0 chlorinity and salinity. You see the value also drop 50% from 14 ppm in 0 degrees C, it dropped to 7. If you increase other parameter in term of chlorinity, means the percentage of chlorine in the water, in the seawater. Salinity, so later I'll give you one equation. Salinity, we talk about the potassium something. Later I'll give you one video about salinity. Okay, so if you increase the parameter also and you check the value in the table, you can see also the value drop almost 50% in all cases. So here it proves you no matter it's a normal water or seawater, if you increase the temperature, it's going to affect the quantity of oxygen in the water. Okay, and you know that oxygen is one of the components that contribute to the corrosion, right? Okay, this is oxygen. What about carbon dioxide and calcium carbonate, right? So carbon dioxide, you know, is CO2. Calcium carbonate is maybe a new term for you. So let's look at one chemical process here. How carbon dioxide contribute to the corrosion? When carbon dioxide combined with calcium hydroxide or CaOH2, it combined with the carbon dioxide, it will contribute, or the products that form under these two elements, it will form calcium carbonate, which is CaCO3 and water. If you're interested to know why this one is so important in natural water, go to the table that I showed you just now. Under the water treatment table, there's one particular item fall under calcium carbonate. There's a special interest in the water treatment. How do you solve carbon carbonate in the natural water treatment? Okay, so this is just to show you how you get carbon carbonate in the natural water. Okay, so there is a element or mineral in the nature that combine with carbon dioxide, it will build or you produce calcium carbonate and water. So you know water also very helpful in when it comes to corrosion. Okay. So sodium, this is another example. Sodium carbonate. Sodium carbonate is different from calcium carbonate, but they show the similar chemical characteristics. Okay. But I give you the sample of calcium carbonate in these slides, right? Okay. Concentration of carbon dioxide in water, you can classify with these four state, right? Meaning you can look at carbon dioxide in the area where how many carbonate you have, or how many carbon bicarbonate you have. And is there any excess of all this? So there are three conditions to check the concentration. So the first classification is you look at carbonate. Second is that from carbonate change to bicarbonate. The third one is bicarbonate in the solution, means maintain in the solution. Or the fourth case is that if you fall in the fourth case, means you have more content of this one, more content of this one, more content of this one. So this is the chemical process that involved with carbonate. What I mean by carbonate, I already show you how to form carbonate. CaCO3. This is how you change carbonate into bicarbonate. So bicarbonate, so if you combine H2O and water, you combine carbon dioxide with water, you get carbonic acid. That's where you get the acid rain. Okay, that's where you get in the industry area. when you have a loss of carbon dioxide, you have a rain fall down, you combine carbon dioxide combined with water, you get carbonic acid. When this carbonic acid it go in contact with limestone, limestone equation is CaCO3, which is the calcium carbonate. All right, limestone is one of the example that have calcium carbonate. So when the acid rain, a carbonic acid combined with the limestone, CaCO3 or carbonate, calcium carbonate, it will form calcium bicarbonate, CaHCO3 bracket 2. Okay, so this is how it affects your pH level in your water when you have different gases. When you have different gases, especially when it come into contact of carbon dioxide, water, limestone. I'll give you an example of question that might come out. I'll give you a scenario where there's a factory having a limestone process industry there. And then the worker found that actually there are some quantity loss in the factory. And the factory actually, when they produce the end products from the limestone, they use water for the equipment. So they use a natural water and all this. Are you able to explain how natural water or how the dissolved gas contribute to the corrosion in the through the natural water condition? Okay, so basically you are looking for keyword carbonate. Are you able to explain the carbonate chemical reaction? How you get bicarbonate? Okay. Okay, I'll show you one video which is more about carbonate and bicarbonate process. This is more in the application of medical, especially when it comes to emergency case. The medical officer, if they're not careful, they might kill you. They might kill you in the solution. So this is a video created by the EMT, emergency medical team, that they want to do some awareness video for all the medical officer when they go in the field. If they do not clean the apparatus, they do not clean the medical devices cleanly, properly, or they do not do a proper treatment of all the medical devices, they're going to harm someone, and even someone going to die because of the deposition of magnesium and calcium salt. Let's see this. If you have a calcium magnesium salt, it's going to form a solid because of bicarbonate process. I'll show you this video. Okay, I will show you one more time the video. This video basically is show you what happened if you change from carbonate, if you mix the wrong calcium and magnesium together, what happened to the results. And all these, they are available in the medical medicine. So if you're not properly clean up the devices, if there are some element in the devices and they pump the solution into the body, you try to imagine all these solids appear in your blood cells and your vessels. It's going to kill you. So let's watch this video again. Next class, we will learn about hardness. I think we stop here with this video. Okay. I end the recording.